Welcome to UV Physics Academy. So here we are discussing how to solve quantum circuits by using our new method. So here I am discussing 3 qubit quantum gates and some quantum circuits. So in the earlier classes we have already discussed a single qubit quantum gates and 2 qubit quantum gates. So I request you please watch that first two lectures if you want to understand that new method properly. Okay, right. Right, so 3 qubit quantum gates are represented by this c square u operation, where u is the single qubit quantum gate, which is represented by unitary matrix of order 2. Let me explain one more time about this new method. For example, you have a single qubit gate. That means this is the qubit state we have, and this is the a single qubit gate. So only one qubit state, that's why we have to write it as a 1. So the operation is represented by, this is u of, it may be x gate or it may be s or it may be t or anything, okay. So it may be h. So u of 0 comma t, t for target. Here the target is 1 because that u is operating on that. So that's why I have written this, just written in that form 0 comma t. So for example, in this case, it will become, I will write here u of 0 comma t. So in this example, we will write it as a u of 0 comma 1. Now you got one more doubt. That is, for example, I have 2 qubit states, but here I have single qubit gate. Then how to do? So 2 states are there. That's why 1, 2. Okay. So 1, 2. Now please take the operations. Starts with that u on 2, that is u of 0 comma 2. After that, whatever the state remaining, that means whatever the state remaining, you have to add, that is plus 1. So just a decimal addition, u of number addition, that's it, 1 comma 3. Okay, right. So that's it, and this is for a single qubit gates. And for example, if you have a 2 qubit, sorry, if you have 2 qubit gates, this is represented by cu, control unitary operation. So let me take, here we have 2 qubit states, and so this is the control bit and this is the target, and here we have unitary operation. This, so controlled operation, that means if c equal to 1, then only this unitary operator, this operator will operate on that target, otherwise it will be as it is, no change. Fine. Okay, how to write this? The operation is represented by, this is u of earlier 0 comma t, but here c involves, that's why what I'm saying is c comma c plus t. So this is the operation, right? So let me take a small example. In this case it is 1 and 2. First you have to write the decimal states, 1 2 3 4, sorry, 1 2 4 8 16, like that. Okay, right. And after that, the operation, this is u of 2 to 1, you are coming from 2 to 1, that's why 2 comma 3, that's it. Now for example, you have 3 qubit states are there, but you have controlled operation from the first top one and bottom one, then give the notation 1 to 4, it is coming from 4 to 1, so that's why this is u of 4 comma 5. Next, whatever the remaining state, okay, so that number you have to add, that is a plus 2, this is u of 6 comma 7. If you already attended this method, you can skip this part and directly go to the lecture. Okay, right. Now let's discuss about this 3 qubit quantum gates. Fine. So this is represented by C square U. That means two control bits are there and one target bit, just like this. So this is the control, and this is the target. So C1 and C2 and one target. Then how to do this? So the meaning of this is both C1 and C2 both are equal to 1, that means on, then only this U will operate on T, otherwise it won't operate. That's it. Okay, so how to represent its operation? One more time, if it is a single qubit gate, U of 0 comma T, and add the number, whatever the number left, you have to add that decimal state number. Okay, next one, 2 qubit quantum gates, that is U of C comma C plus T. Now here we have 3 qubits, 2 control bits and 1 target bit. The operation is represented by U of, okay, so C1 plus C2. That means both must be on. What is the meaning of C1 plus C2? You are considering both C1 and C2. That means both are on. So C1 plus C2, comma, it is operating on T. That's why C1 plus C2 plus T. That's it. In this example, 1, 2, 4. Then the operation in this is represented by U of, so 2 plus 4, 6, comma 6 plus 1, 7. That's it. So it will affect only that 6 and 7 states. Don't get tension, this is a decimal notation. 6 you can write it as a 110 later, and 7 you can write as a 111 later. So because if you are doing the algebra in that decimal notation, so I feel it is a little bit so easy to get the final state. That's it. Okay, let us take an example. So what is the meaning of this? So here we know what is U. U is nothing but A, B, C, D, a single qubit quantum gate. The first column stands for the amplitudes corresponding to off state, and second column for on state. I told you already, first number is off, second number is on in that operation. Always first one is off, second one is on. Okay. What is the meaning of that? That a target. See, if these two are on, you see, you will get clarity. These two are on. This target is off. What you will get? 4 plus 2, 6. 7 on. What is the meaning of 7 on? Target is on. Target is on. Here, what is off and what is on? Target is on. If target is on, 4 plus 2 plus 1, 7. That's it. Okay. All right. Now I'm going to write this sixth one. Sixth is off. That's if it operates on this gate, what you will get, A 6 plus B 7. So it creates a superposition state with amplitudes that corresponding to that first column. And 7 operates on this U circuit, okay, I mean quantum circuit. You have to take the second column. The reason is 7 state is on. So that is a C 6 plus a D 7. So that's it. So finally this is a C square U, that means 2 controls and 1 target. Maybe later you will get one control and 2 targets also will be there. So that's why I have written like this. Okay, fine. Now let us take some examples. So first one I am taking U equal to X. That implies it becomes C square X, and this is nothing but Toffoli gate. Right. Okay. Now this is nothing but, here you have 3 quantum bits, sorry, 3 quantum states. In the place of X, in the place of U, you have this X gate 1, 2, 4. Okay. So the operation is nothing but X of, because here the unitary operator is X of 4 plus 2. 6 comma 6 plus 1 7. That means it flip 6 to 7 and 7 to 6. That's it. Okay. Next, let us take a few more examples. So let us take two more examples like this. Now give the decimal notation 1, 2, 4. Okay. So here two controls are there, that is 1 and 2. So that's why this is x of 1 plus 2, that is a 3 comma 3 plus 4 7. So it will flip only 3 and 7. So 3 to 7 and 7 to 3. Right. And come to the next one. Here also again we have to take a 1 to 4. Okay. So now the two controls, that is a 1 and a 4. 1 plus 4 5. So this is a 5 comma 5 plus 2 7. That means it will flip only 5 and 7. The remaining states are as it is. Okay. Right. So let us take another one. So for example, so here let us take another 3 qubit quantum gate. So one control and two targets. Okay, so this is a control and here we have two targets. So how to solve this? This is equivalent to like this. So the first one is here and the second one like this. So successive operations. Okay, so let us apply 1 2 4. Apply our technique. So this is the first one, this is the first one. Now this is u of 4 to 2. That's why 4 comma 6. But what is remaining? 1 is remaining. So that's why plus 1. If you add plus 1, u of 5 comma 7. Close. Come to the next operation. This one. So this is coming from where to where? 4 to 1. That's why u of 4 comma 5. The remaining is 2. Please add 6 comma 7. That's it. So this is off, on, off, on. Let us take one example. Now here I am taking, so one control and two targets. Here I am taking X gate. Okay, right. So this is nothing but CX, I mean control not, and one more control not. So 1 2 4. Okay, so please take the first operation, that is X 4 comma 6, add 1 5 comma 7, next 4 comma 5, add 1 6 comma 7. That's it. Okay, so now here I will tell you a small technique here. Wait a minute. So here let me take the states like this. If I take 4 5, now please apply the operations. 4 to 6, 6 to 7, that's why 4 becomes 7. Next 5 to 7, 7 to 6, that's it. Okay, so again if you want to check that 6 and 7, otherwise take the 7 and 6 again, you will get the reverse. That means 4 5. So finally we can write this as x of 4 comma 7 because it is flipping 4 and 7. Next one, x of 5 comma 6. That's it. So if you have two, I mean if this sees one control and two targets, that two target a single qubit gates are equal to x. So here it is a Pauli, sorry, here it is a Pauli x gate. Okay, then we are getting this answer like this. So we can write directly. So this is x of, this is a possible only when u equal to, this u equal to x, that is 0 1 1 0, not for all, only for x. So this is nothing but, here we have t1 and this is a T2 and this is a C. So this is nothing but C comma C comma C plus T1 plus T2, C comma C plus T1 plus T2, x of C plus T1 comma C plus T2. Wait a minute. This is a direct operation only when only it is possible when that u equal to here, this u equal to x. For example, if you have two S gates or T gates, it is not possible. This is only for that u equal to x. So still not understanding. Wait a minute. For example, I have like this. Okay, once again I am taking this two x gates here and one control. So 1, 2, 4. So directly we can write x of 4 comma 4 plus 2, 4 plus 2 plus 1, that is 7, and x of 4 plus 1, 5, comma 4 plus 2, that is 6. This is what I am saying. Same answer. But this technique please apply only when you have two same x gates there. If one u is if the u is s or t gates, don't apply this. Okay, right. So next another 3 qubit quantum gate, Predican gate. This is a CU swap. So here you have a swap gate. Let us say this is S1, sorry, S1 and S2. Let's just interchange this S1 and S2. Okay, but here you have C swap gate. That means if control bit is equal to 1, then only a swap will exist, otherwise no operation. Okay, fine. Let us say this is S1 and S2. Now how to operate this? Carefully see operation. This is I'm taking just F letter of C comma. That means if C is on, then only operation occurs. So that is a C sorry. So C plus S1 comma C plus S2. Only these two states will swap. So for example, in this case, it is 1, 2, 4, then the operation Predican gate. So this is a 4 plus 1, 5, 4 plus 2, 6. So only the swapping is between 5 and 6. Other states are as usual. Okay. So I hope you understand. Still not understanding, one more example. Let us take 4 qubit states, and I am taking, here is the swap gate. Okay, so this is the control bit. Now give the notation 1, 2, 4, 8, right? Okay, so now take the operation. It is 8, 2, 1. So this must be on. That's why 8 plus 1, 9. Anything you can add, but not this 4. Okay, so you have to add either S1 or S2. So 9 comma 8 plus 2, 10. Okay, next this 4 is remaining if you observe carefully. So as usual, same method. Earlier we have added that 4. So this is a 13 comma 14. That's it. Okay, that means it flipped 9 to 10, 10 to 9, and 13 to 14, and 14 to 13. Clear? Right. So next let us take this equivalent circuit. Now we want to show that these two are equivalent. This Predican gate and this one both are same. Okay, let us start. Now here I am taking the decimal notation 1, 2, 4. First let me check this operation. This is f of, just for my understanding I am just taking that letter. Okay, so it represent a swap gate only. You can write yes a swap also, it's okay. F of 4 plus 1, 4 plus 1, 5, 4 plus 2, 6. That's it. Now let us check. Here we have control not gates. Okay, 1, 2, 4. So this is the first x, that is 1 2 2, 1 comma 3, and 4 remaining you have to add. So don't forget to add the remaining state. Next one we have c square operation. I hope you know that also. So c square means 4 plus 2 6, comma 6 plus 1 7. That's it. Next one is also from 1 to 3, sorry 1 to 2, that's why 1 comma 3. Next one 5 comma 7, we have to add 4. Now carefully check. So here if you observe carefully, from right side we have x of 5 comma 7, from left side also we have 5 x of 5 comma 7. That means it will flip, if it is on right side it flip rows, fifth row and seventh row, and left side it flip fifth column and seventh column, interchange, sorry not flip, interchange. So that's why this 7 is replaced with 5. 7 is replaced with 5. Now the remaining is x of 1 comma 3, x of 6 comma 5, and x of 1 comma 3. Now you can bring this side, because here there is no common number. If there is no common number, they commute. I repeat, if there is no common number, they commute. So you can interchange the positions. Then x13, x13 cancel, and the remaining is x of 6 comma 5 or 5 comma 6. Anything you can write, it's not a problem. That's it. So both are same. Let us take one more circuit. Right. So this is also a very interesting one. So you have to show that. So both the circuits are equivalent if this v square equal to x, Pauli x gate. Okay. So we have to show that these are equivalent. Now first let me take this operation 1 2 4. So this is the swap gate. Okay. So 4 4 plus 1, that is a 5. 4 plus 2, that is a 6. That means it will swap 5 and 6. If you want, you can write in the binary notation 101 and 110. Now let us check this. Here, this is a very nice one. Please check 1, 2, 4. Now let me write the operations. First we have x, that is 1 2 2, 1 comma 3. Add the remaining, that is 5 comma 7. Next control v, you can write v of, no issue, 2 to 1, that's why 2 comma 3. Add 4, 6 comma 7. Next again control v, this time 4 to 1, that's why 4 comma 5. Next add 2, that is 6 comma 7. Next again c naught is there, that is a 4 to 2, 4 comma 6, and you have to add 1 this time, 5 comma 7. Next again v dagger. Okay, so v dagger is there. This is from 2 to 1, that's why 2 comma 3. You have to add 4, 6 comma 7. Let me take this side. Right. Next one. Again c naught 1 to 2, that's why 1 comma 3, and you have to add 4 or 5 comma 7. Next again c naught, this time it is from 4 to 2, 4 to 6, and add 1 of 5 to 7. That's it. Now carefully observe. No need to worry. It's easy only. No need to worry. Now here we have, sorry, this v dagger, this one v dagger, and this is also v dagger. Right. Now carefully observe. Here in this, sorry, in this, we don't have 2 comma 3. There is no 2 comma 3. So then you can write this v dagger to this one. You can write this v dagger 2 comma 3 here, and these two will commute. These two will multiply. V into v dagger equal to I. So finally we can write, just to cancel these two. That means 2 comma 3 operation over. Next check one more. Here we have x 5 comma 7, x 5 comma 7, x into x, I. So leave it. Next still anything is there? Yeah, one more is there. So if you observe carefully again, after cancelling this 2 comma 3, 2 comma 3, and here there is no 1 and 3, no 1 comma 3. That's why this x of 1 comma 3 you can write here. These two commute and that also gone. Now let me write what is the remaining. X of 5 comma 7, and here I have uh, v of 4 comma 5, this one I am writing, and after that these two are side by side, v of 6 comma 7, v of 6 comma 7. I can write this as v square of 6 comma 7. Next 4 comma 5 I have written, and after that x of 4 comma 6, x of 5 comma 7, and after that v dagger 6 comma 7. Okay, and anything remains? Yeah, one more is there. Yeah, so here again x of 4 comma 6, the last one. So that's it. This is what we get. Now carefully observe. Already they have given v square equal to x. So that's why I can write this as x of 6 comma 7. Now fine. Now carefully observe. This is 5 to 7 and 7 to 5. This is a 5 to 7 and 7 to 5. That means uh, fifth row and seventh row interchange, fifth column and seventh column interchange. That's why this 7 is replaced with the 5 and this 5 is replaced with the 7. Clear? Then this operation gone. V of 4 comma 7, sorry, x of 6 comma 5. Next, what is the remaining? Still we have one more, this here. Here we have 4 comma 6 and 4 comma 6. So that's why 4th row, 6th row interchange and 4th column and 6th column interchange. So cancel the operation. 6 is replaced with 4. So the remaining is V dagger 4 comma 7. Clear? Now, so I request you please check. This is a V and V dagger I. So the remaining is x of 6 comma 5. That means 5 and 6 are sixth states are interchanged. That's it. Okay, so this entire circuit, the right side circuit, this is equivalent to this Faradican gate if v square equal to x. Okay, so this cancellation is easy, it's not at all difficult. Just see the numbers. If there is no common number, you can write, you can check, you can take the commutation law. Okay, so here earlier we have discussed one control and two targets. Let us take two more examples. Now in this case I have taken u as z, that is 1 0 0 minus 1. Okay, so 1 2 4. So here what you have to take, how to take it separately. So this is the first control z and this is the next cz operation. Then it is 1 2 4. So first one z of 4 comma 6, that means a 4 to 2, and you have to add 1, that is a 5 comma 7. Next z 4 comma 5, you have to add 2, that is a 6 comma 7. Now let me take a 0 1 2 3. Here there is no 0 1 2 3, that's why it is as it is 0 1 2 3. And next I am taking 4 5 6 7. You know that this is off and on, off on. Now just go from left to right. 4 off, no issue. Next again 4 off, no issue. Next 5 off, but second 5 it is on, minus 5. Next 6 off, sorry, 6 is on, minus 6, but the next 6 is off, that's why no issue, minus 6. 7 first operation on, again on, minus minus 7 plus 7. That's it. Still not understanding? So this is equivalent to first control S gate, and again one more control S gate, 1 2 4. So this is S of 4 comma 6, add 1 5 comma 7, next S of 4 to 1, that's why 4 comma 5, add 2, that is 6 comma 7, off off on. Okay, right. So this is the first column for off, second column for on. Right. So here also I am taking 0 1 2 3, and there is no 0 1 2 3 involved in this operation, so that's why 0 1 2 3 remains as it is. Next 4 5 6 7. So here 4 is off, no issue. Here also 4 off, no change. Next 5 off, but here it is on, that's why I5. Next 6 on, and here off, one time on, that means I6. 7 two times on, I7, again one more I, that's why -7. That's it. Okay, right. So next let us discuss about this anti-control quantum gate. So here we have two qubit states, okay, and this is a unitary operator. So earlier we have seen this control operation, okay, but here take a hollow circle like this. So that means this is the control bit and this is the target bit. If control bit is a 0, then only you will operate on target state. Otherwise, it won't operate. It will be as it is. That means initial state is a C. Let us take like this, and this gives if C is a 0. So C as it is, and U operates on T. All these when it will be possible only if the control bit is 0. That is called anti-control. So if you take this is example 1 and 2, two states are there, that's why I'm giving I have given this decimal notation, and this can be written as U of 0 comma 1, but don't add that 2. Why you are not adding that 2? Because that is off. See, this is off, that means that is a 0. So you need not to add now. So wherever unitary operator is there, you just take that 0 comma target. Now you got a doubt. Earlier you have written like this. So single qubit quantum gate you have written like this. This is a 1 and a 2. Okay, maybe you got this doubt. You have written U of 0 comma 1, and here also you have written 0 comma 1. Yes. Here in this case, the operation is not only U of 0 comma 1, and one more is there. You have to add plus 2, that is U of 2 comma 3. But here no addition. So the only operation is U of 0 comma 1. Okay, right. So I hope you understand this difference. Now let us take some examples. So here I have this 3 qubit states. Now I'm taking anti-control, control, and this is U, something like this, right? So you may be a single qubit gate operator. You can take A, B, C, D like this, unitary operator. So here I have 1, 2, 4, right? So now here is a control, and this is the anti-control. So earlier how you have done that control, you do the same thing. That means U of, this is a 2 comma, it is 2 to 1, that's why 2 comma 3. But don't add 4 now, that's it. Anti-control, don't add. So here, because of this anti-control, don't add. That's it. And take one more example. Here you have unitary operator, single qubit gate, and here anti-control, but this time this is the control. See that a dark circle as a control and hollow circle as an anti-control. So here we have this decimal notation 1, 2, 4. Right. So here a control is a fourth one and anti-control is second one. So wherever you have control operation, just to follow the same operation, that is u of c. C is here, it is a 4, 4 to 1. That's why a 4 comma 5. But now don't add 2. That's it. That is what I'm saying. So take some more examples and let us take here we have u and this is control and this is anti-control. 1, 2, 4 and this is control and this is anti-control. So this is u of 2 to 4. So that's why 2 comma 6 and don't add 1. That's it. Next take one more and here we have yeah, anything you can take, it's not a problem. And this time I'm taking here anti-control and this is a control here I'm taking. So 1, 2, 4. This is u of 1 to 4. That's why 1 comma 5, but don't add 2. So just here I'm writing don't add 1 and here don't add 2. Right. So the only difference between earlier operations and this operation is earlier we have added whatever the state decimal state remaining we have added, but now don't add that. That's it. Okay. Right. Right. So let us take a few more examples. Here unitary operator we have taken as x. Okay. So I'm giving the decimal notation 1, 2, 4. Here this is x. This is x of it is coming from 2 to 1. That's why it is simply 2 comma 3 and no more addition of a 4. So this is x of 1, 2, 4. This is nothing but 4 comma 5. And this is 1, 2, 4. This is a 2 to 4. That's why 2 comma 6. And this is 1, 2, 4. 1 to 4. It is a 1 comma 5. So no more addition of 2. Right. Right. So let us take a few more examples. Okay. So here we have 3 qubit states. That's why 1, 2, 4. Right. And now I'm taking this operations x of 4 to 1. It is a 4 comma 5. X of, see, 2 controls are there. So that's why 4 plus 2, 6. Wait a minute. Yeah. 4 plus 2, 6 to 1. That's why 6 comma 7. Next again here 2 controls are there, 1 and 2. So that's why 3 comma, sorry, 3 comma 7. Next x of 1 control and 1 anti-control, that is a 4 to 1, 4 comma 5. So any cancellation? No, just proceed. So here 0, sorry, 0, 1, 2, 3. If this is the initial state, so 0 no change, 1 no change and 2 also no change, but 3. So please check the operations from left to right. 3 here, 3 to 7, but see, after that there is no 7. Remember, you have to travel from left to right. So now you got a 3 here, 3 becomes 7. After that there is no 7, but you will get a doubt. So before the 7 is there, no, the operations won't go backward. So right, left to right, time travel, left to right. Okay, so this is 3 to 7. So that's why it's a 7. Next 4, 5, 6, 7. Now see, first 4 become 5. Next check any 5. Yes, here last 5 is there, 5 to 4. Like that you have to come from first operation to last operation. And next 5, 5 become 4, 4 become 5. Next 6 to 7, 7 to 3, 7 to 6. That's it. Okay, so in the output state also, no state will be repeated. That is the indication. If any number is repeated, maybe you have done wrong, you have done mistake. So that means what I'm saying is 0, 1, 2, 7, 4, 5, 3, 6. No state will be repeated again. Okay, all right. So we can do this in a easy way also. Let me explain another way. So here we have written the operations. One more time let me take. That is x of 4 comma 5, x of 6 comma 7, and x of 3 comma 7, and x of 4 comma 5. So earlier I told you commutation relations. Okay, so now so here this does not contain any 4 comma 5, no 4 comma 5. So that's why you can bring this side and side by side x 4 comma 5, x 4 comma 5 cancel, that is I. So the only remaining is a 6 7 and 3 7. So that means only changes occur between 3 6 7. Yes, exactly. See, 3 becomes 7 and 6 become 3 and 7 become 6. So like this you can do it directly. Now if you take 3, 3 becomes 7 over, and if you take a 6, 6 to 7, 7 to 3, and if you take 7, 7 become 6, like this. Okay. So the remaining states no change, 3 to 7, 6 to 3, no reverse arrow, be careful, 3 to 7, 6 to 3, and 7 to 6. The remaining will be as it is. And see the next one, 1 2 4. So here I'm taking the operations. So here x of 2 controls are there, that's why 6 comma 7. Next x of 4 to 1, that's why 4 comma 5. X of 1 and 2 are control bits, so that's why 3 comma 7. I hope you understand this method. And here 2 is control, 4 is anti control, that's why 2 comma 3 only. That's it. Now any cancellation here? No, here there is no cancellation. 0 1 2 3. So just check any common. See here why these two commute means there is no common number. Again 4 5 and 6 7, why they commute means there is no common number. If there is no common state, common number means common state, then take a commute. Right. So here a 0 no change, 1 no change, 2 yes. So here 2 to 3, but don't come back again please. 2 to 3. Next 3 to 7, 7 to nothing is there, that's why 7. Next 4 5 6 7, 4 to 5 and 5 to nothing. So 5 to 4, that's it. Next 6 6 to 7, here 7 to 3, here 3 to 2. Once again it's nice, please check again. You are taking 6 6 to 7, 7 to 3, and 3 to 2, so that's why finally 2. Next 7 7 to 6, and after that no operation, so that's why 6. And check any number is repeated, nothing is repeated, that's why almost, that means you have done correct. Right, let us take another one, 1 2 4. So here anti-control, and this is anti and this is control. So two controls here, anti-control, right? Okay. Right. So both are anti-control, that means a 0 only. Here x of 0 comma 1, right? Because only x is on 1. So next after that one control is there, that is 1. It is coming from 1 to 2, that's why 1 comma 3. Next x, two controls are there, 3 comma 7. One control is there, 1 comma 3. So no, I mean both are anti-control, that's why 0 comma 1. Now let us see. Here you have to apply another cancellation rule which we have already discussed earlier. Still, if anyone not understanding, please check. Now carefully observe. Here this is the operation, some operator or some matrix, whatever it is, some matrix which is, I mean operator is represented by a square matrix. So this side you have x of 1 3, this side you have x of 1 3. What is the meaning of that? One more time I am explaining. If this is the matrix, if you consider, the right side 1 will interchange the rows of 1 and 3, and the left side 1 will interchange 1 and 3 columns. So that means what? 1 and 3, first row and third row will interchange, first column and third column will interchange. Means here if you have 3, that 3 stands for third row, third column exists. So that 3 will be replaced by 1. This is the advantage in this decimal notation method. So directly some cancellations, some commutations, all these things we are understanding very clearly. So I hope you are following. So these two operations gone. Next, see again quite interesting. X of 0 comma 1 and again x of 0 comma 1. Now you please check. So this side and this side operation, left and right operations must be same. Then only you can do this. So here x of 0 comma 1 and here x of 0 comma 1. That means here 0th row means R0 you can take. So okay, so no need to get tension. 0 and 1, R0 and R1 will interchange, C0 and C1 will interchange. So that's why this 1 will be replaced with a 0. So finally x of 0 comma 7. I think this question is in this Nelson and Chong book. I think this is very easy to handle this type of problems with this algebra. Actually, if you want to do the original method, you have to take that matrix form and multiplication. And I feel this is a little bit easier than that matrix multiplication. Okay, right. And here one more, 1 2 4. Still not understanding, please check. Now here I'm writing the operations, that is x of 2 control, 4 anti-control, that's why 2 comma 3. And here 1 and 2 are control, that's why 3 comma 7. So very easy. And here 2 control and 4 is anti-control, that's why 2 comma 3. Now you please try this. Pause the video for a few seconds and please try to do it yourself. So here 2 3, here 2 3 is there. So second R2 and R3 will interchange, C2 and C3 will interchange. So that's why here this side R operations, row operations, and this side column operations. That's why 3 is replaced with the 2. That's it. Okay. Here one question was given in the some exams. Okay, in one of the exam, uh, U operator is given, and here 3 qubit states are there. One quantum circuit is given. So here we have anti-controls A here, and yes, fine. This is the circuit given. They are asking what is the output for this 0 0. In our method, you can find the output of any state, any initial state. That means out of here 3 qubits are there, means we have basis states from 0 to 7. So anything you can find. So they are asking for 0. Let us find. But I am writing the operations for all the states. Okay. So if you want only 0, then you can write u of 0 1 only. But I am writing all the things. Please try to follow. So u of 0. Oh, I'm sorry. I have to give the decimal notation 1, 2, 4. Right. So this is u on 1, that's why u of 0, 1. Now we have to add, right. So you have to add 2, that is 2 comma 3. And again you have to add the remaining state, that is u of 4 comma 5 and u of 6 comma 7. Right. That's it. Uh, Fine. And now let us go to the h. So h is on 2, so that's why 0 comma 2. So why you are not taking that anti-control? I told you already what is the meaning of anti-control. Don't consider that, it's off, so don't add that 1. So next the remaining is a 4, that's why add 4 only. Next x it is there, but two anti-controls are there, but it is on 4, that's why 0 comma 4. But don't add 1 and 2. Okay, right. So I hope you got it. Now they are asking for initial state 0, that's why I'm taking a 0 only. This is very nice, please check. So 0 is operating, I mean u is operating on 0. So here it is off, here it is on. Now please check where is this 0 in the operations here. That is u of 0, 1. That means it creates a superposition state of 0 and 1. So with amplitudes of a first column, root 2 by 3, 0 plus 1 over root 3, 1. Nice. Now after that head mod operation is there. So I'm taking like this head mod operations. So please check, and 0 and 1 here. It creates a superposition of a 0 and 1. So that's why, sorry, 0 and 2. That's why root 2 by 3. This is 1 over root 2, 0 plus 2, because it is off, on, off, on. 0 is off, close, I mean bracket close, 1 over root 3. Okay, so there is no 1 here, so leave it. That means head mod, it won't create anything, I mean it won't operate on that 1. So whatever the numbers you are seeing here, so head mod will change with those states only, 0, 2, 4, 6 only, no other states. I hope you got it. This is the advantage of this method, right? And this root 2 gets cancelled, and I'm just writing one more time. This is a 0 plus 1 plus 2, right? And finally there is one more operation, that is x, that becomes 0 to 4. That's why 4 plus 1 plus 2. That's it. So this is the final answer. So if you want to do with the if you want to do mathematically, you have to find the matrices and multiply with the initial state, that is 1 0 0 0 0, so on. So because initial state is 0 0, tensor product of 0 0 0. Okay, right. So first please see this first circuit. Here is one more quantum circuit, and carefully observe here. Whenever you have x, control, and x, one more time. So this is here we have x, and this is the control, and x. This is nothing but anti-control. So this is what we get, anti-control. And after that x is the same here, this one. And after that control h, swap gate, and again here the top one. Again you got anti-control. So now I'm going to write the operations for this, that is a 1 and a 2. Okay, so let me write the operations. So first a head mod, that is h of 0 comma 1 and no addition, x of 0 comma 1 you have to add 2, 2 comma 3, and control h. Okay, so whenever control h is there, control to target 2 to 1, that's why it is a 2 comma 3. No more addition, swap. I'm taking SW, that is 1 comma 2 or a 2 comma 1, anything, it's okay, no issue. Or you can write x of 1 comma 2, it's okay. Swap 1 comma 2, you please write x of 0 comma 1 and add 2 comma 3. Next anti-control header mod, that is a 0 comma 1, x of 0 1 and add to 2 comma 3. So next control header mod, that is a header mod of from 2 to 1, that's why 2 comma 3. Okay, all right. So finally, once we got these operations, I'm taking this 0 1 2 3 at a time I'm taking. So now this is the header mod. So 0 becomes 0 plus 1, 1 become 0 minus 1. There is no 2 as usual and 3 as usual. After that, x operation is there, 0 become 1, 1 become 0, 1 minus 0, 2 become 3, 3 become 2. Next head mod is there, 1 plus 0 as it is, 1 minus 0 as it is, 3. 3 is a linear combination but is on state, so that's why 2 minus 3. 2 is off, 2 plus 3. Next swap gate. So sorry, 1 and 1 to 2 swapping, that is a 1 become 2, so 2 plus 0, 2 minus 0, 1 minus 3, 1 plus 3. Next after that x, so 2 plus 1, sorry, one more is there, please check. So 2 become 3, 0 become 1, 3 minus 1, 1 0, 3 2, 1 become 0, 3 become 2. Next again header mod is there. Okay, so you have to take the one more time header mod operation, but unfortunately, yeah, so this is 3, 1 is off, so that's why 0 minus 1. I'm not taking any normalization constant, finally I will take. So 3 minus 0 minus 1, 0, 0 plus 1 because off state, minus 2 as it is, and 0 plus 1 plus 2 as it is. Now this head mod over, after that some other operation is there, that is x. Still continue. So 3 as it is, and 0 become 1, 1 becomes 0. Oh, sorry. 3 become 2. Careful, you have to observe careful. 3 become 2. Next 2 minus 1 minus 0, 0 to 1, 1 to 0, 1 plus 0. Next minus 2, 2 to 3. Yeah, carefully check. 1 plus 0 and plus 2 become 3. And after that one more head mod is there, so that's why 2 is off, 3 is on, so 2 plus 3 plus 1 minus 0, 2 plus 3 minus 1 minus 0, 1 plus 0 minus 2 minus 3, 1 plus 0 plus 2 minus 3, because 3 is on state. So finally we got a 4, that's why the normalization constant is 1 by 4. The next one is I think that's it. Already we have done all the 4 states, sorry. I thought that I have done only 2, I can give the homework to you, but it's okay. So I request you please check one more time. If any correction is there, please inform me, right? Right. So this is quite interesting one. So here they have given c square x operation. That means c square x gate, sorry. This is nothing but a Toffoli gate, okay, and they are asking to show that this is equivalent to this given circuit, okay, right. If you want to do with matrix algebra, it takes so much time, and let us do in a different way, okay, right. So first let us check what is this operation here. 1 2 4, so this is nothing but 4 plus 2 6, 6 comma 7. That means it flip only 6 and 7 and the remaining as it is. So here also we should get the same thing, okay. Now carefully observe the circuit, don't bother about that so many gates are there, how to do. Here I will tell you a beautiful technique, all of you please see. Now here there is no connection between 2 to 1 from here. Observe, from that line onwards there is no connection between 2 and 1. So that's why whatever the gates you have on 1, you can bring this side. That means what I'm saying, you can take this as separately and two T and H, the last T and H this side. That means like this. Of course, in this second part also you have one, okay, and this is I'm dividing this as a two parts, okay. So one more time, and this is the first part, and this is the second part. Okay, ready? Now I'm taking the first part. Here I will tell you a small technique. Whenever, if you observe carefully, all the gates are on that first state, first qubit state 1. So whenever you are having this type of situation, my suggestion, please take it as a psi. And let me take that circuit separately, then you will get, then you will understand properly what I'm saying. So here, right, so this is what I'm saying. After that you have T and H here, so you can bring this side because there is no connection between 1 and a 2. So here it is a uh, T and here it is H. I'm not drawing that boxes, it's okay. Now this is 1 2 4. Now carefully see, if all the gates are in a single state, that means one state here, then you please take it as a psi. Then instead of taking this 1 and 2 4, you can take only these two, that is 1 and 2. Okay, then this 1 and 2 will form 4 bases, that is a 0 1 and a 2 and a 3. That means both off, 1 on, 2 on and 3 both on, like that. So here input states, if you have any confusion, your input states will be 0 psi, uh, 1 psi, 2 psi and 3 psi. So what about psi? Psi is a combination, it may be 0, it may be 1, later finally you can check it. You can take 0 once and you can take 1. So because this will solve very easy, I mean it will take less time, otherwise it takes more time. If you take 1 to 4, so many operations will come. This is one of the advantage whenever all the gates are here. Okay, fine. Now let us start. So here I'm taking a 0 and psi, first input 0 and psi. Now carefully see, the entire circuit is operating on this 0 psi. Whenever it is a 0, for both are, that means both are on, sorry, both are off. That's why no control operations, no control operations. So only we have 0 as it is. And here the operations, listen carefully, we are multiplying the matrices. That's why I request you, earlier operations and here we are multiplying the matrices. That's why I have to write from right to left. Maybe if you are following that tensor product notation, top to bottom tensor product you will take, right to left ordinary matrix product you will take. So like that you have to take right to left. Don't get confusion. Earlier operations method we are not doing here. The reason is it takes so much time, and if you take psi here and apply like this, it takes very less time. Please check. Please check. Right to left. That's why H T, no X. The reason is it's off. So T dagger, T, T dagger, H and psi. Now this T dagger, T dagger, that is I, okay, and H into H, that is I. So finally we got 0 psi. Still one more if you are not understanding. So this is 1 as it is because no gate is on that 1, okay, that's why 1 as it is, and psi. So H, this time which is what is on, this 1 is on, okay. So then this C naught and this C naught will be operating on that side. H T, this is off, okay. So no X and a T dagger, yeah, this time it is X. I hope you understand. This one no, next one no, next T dagger, next one S, that is X, H, psi. Okay, now carefully observe. So again here we have t dagger x x I h h I, that is one psi. Next, still not understanding, 2 psi. Now this time this 2 is on, that means which gate? This gate, this gate will operate on psi. So 2 as it is, because there is no gate on 2, on 2. That means now next one h t, okay, yes, this time x is on, t dagger, next x off. The reason is it is here it is a 2, 2 on, 1 off. Next again t, next x on, next t dagger, and x off, and h psi. So here also t t dagger I, x x dagger, everything gone. That's why a 2 psi. And the last one is, it's quite interesting. And if you have this 3 psi, now carefully see. This is nice. So here there is, I mean 3 means both on, both on. So no gates on 1 and 2. That's why no need to bother. Only bother about that psi. So here all C naught gates will operate because both 1 and 2 on. So right to left, H, T, X, T dagger, X, T, X, T dagger, X, H, psi. Now carefully observe. See, I told you earlier, X operator X from right side and left side, that means rows and columns will interchange. So please identify that. Yes, this is easy. So T dagger I have already written there here. So right side x is there, left side x is there, means both the rows and columns are interchanged. That means the diagonal elements will interchange. I hope somewhere in the earlier videos I told you this technique. So finally here there is no space, that's why I'm writing here. So here h, okay, and I'm checking this only first. Leave that h, okay. So here this is t. So t, that is 100 e raised to I pi by 4. Next x t dagger x. So please go to t dagger and interchange. So that is e raised to minus I pi by 4 0 0 1. And next again t is there, 100 e raised to I pi by 4. Next again x t dagger x is there, that's why e raised to minus I pi by 4 0 0 1. All are diagonal matrix, happily just multiply that corresponding elements, okay, no need to do all these mathematics. 1 e raised to minus I pi by 4, 1 e raised to minus I pi by 4, this will become e raised to minus I pi by 2. Just multiply that corresponding elements because all these are diagonal elements. So sorry, diagonal matrices, 0, and here also 0, and here e raised to I pi by 2. So this is nothing but minus I 0 0 I. I can take minus I common, okay. So this is quite interesting. If I take minus I common, this will become 100 minus 1. Oh, this is nothing but Z. So finally here you have H and here you have H. So minus I outside face H Z H, which is nothing but X. So this is minus I X. So finally the answer is this 3 psi become minus I 3 x psi. This is not the final one, actually second one is there. So you have to combine both the operations. So at a time I'm not taking because here one method I'm applying, and for the second part I will take another method. The reason is there all the quantum gates are not on a single state. So both 2 and 4 it is having some quantum gates, okay. So now let us take the second part and combine both the answers. Now carefully see one more time. Here 0 psi no change, 1 psi no change, 2 psi no change, and 3 psi minus I 3 x psi. Okay, that means uh, if initial state is a 3 psi, it will convert to minus I 3 x psi. If psi is a 0, it will become 1, psi is a 1, it will become 0. Right. Now let us take the second part, and here this is a psi as it is. Now I am taking 1 and 2, but here I am taking the operations because both 1 and 2 are having that quantum gates. Okay, so operations from left to right. Okay, right. So this is x 2 comma 3 and t dagger 0 comma 1 and t dagger 2 comma 3. Next again x 2 comma 3, and here we have two t gates. One is on 2, anything you can take, it's not a problem. T01, T23, and one more t on 2, that's why 0 comma 2, and add 1 1 comma 3. Now please apply the technique whatever earlier we have used. So this is a 2 3 2 3 interchange, but right side and left side is there, so that's why second row third row will interchange. I mean r2 r3, not second and third, r2 r3 will interchange, c2 c3 will interchange. That's why here 2 will become 3, 3 will become 2. Next after that, here there is no 0 comma 1, so that's why already this is gone. Actually in this there is no 0 comma 1, that's why you can bring this t dagger 01 and a t01, you can bring side by side and these two gets cancelled. And finally we left with t dagger 3 comma 2 t sorry t 2 comma 3 and next t 02 t 13. So this is what we get. So remember, maybe here you will get one doubt. So shall I cancel these two? The answer is no. Sir, if it is x, shall we cancel? Yes. X23, x32 both are same, but t dagger 32, t23 both are not same. So because here 3 is off, no phase, and here 2 on, and here 2 off and 3 on. That's the difference. Okay. So then how to do this? I am taking again initial state. This is for second part of the circuit. Okay. And finally I will combine both the first part and second part. Final answer I will combine. 0 psi become, so here no operation on psi is safe, and only the operation is on first initial state 0. So here there is no 0 first, second no 0, here we have, but it is off, that's why 0 as it is and psi is as it is. This is the circuit output. And one psi, so here there is no 1 and here 1 off, that's why no change. Okay, next 2 psi. Okay, careful. So here we have 2 on, that's why e raised to minus I pi by 4, because it is a 2 dagger. 2 psi. Next again 2, sorry, again t, but it is off, no change. Next again 2 on, that's why, but it is, this time it is a t. I think it's better to write like this. I think multiplying it's not good. Now let us try this. So here 2 on, that's why t dagger. Here 2 off, no t, and here 2 on, that's why t. This is better. So this is I, no change. Next this one, careful, 3 psi. Okay, now here 3 off, that's why no need to write t dagger, but here t, I mean 3 on, that's why t, and here on again t square. That's it. Okay, so finally you got a t square means e raised to I pi by 2, because the t, you know this one, e raised to 100 e raised to I pi by 4, t square e raised to I pi by 2, which is I 3 psi. Now let us combine all the things. Now I am taking a final both 1 and 2, first part and second part. So initial state 0 psi, the first part, let me check, there is no change, and second part also no change, and 1. So first part no change, second part no change, and similarly 2 psi, first part no change, and the second part of the circuit no change. But here third one, so the first part make it as a minus I 3 psi, and the second part make it as a I 3 psi. That's why minus I, that is a 1 only, so 3 psi. Sorry, I'm sorry, 1 minute, I'm sorry. Yeah, right. So here this first part makes minus I 3 x psi. Be careful, minus I 3 x psi. Next second part make uh, 3 psi. That means 3 become I3. Here already minus I, here I is there, so that's why it become 3 only, and x psi as usual. So finally the operation, this is a 3 psi become 3 x psi. Now you please give the option. So for example it is either 0 or 1. Okay, so here it is a 3, this is a 0. So here we have 2 qubits, that's why 2 3s are 6 plus 0 6. Okay, and here 2 3s are 6 plus 1 7. Okay, so then it become, so here for 0 it become 1, and for sorry, for 1 it become a 0. So that's why 2 3 is a 6 plus 1 7, and 2 3 is a 6 plus 0 6. That's it. That means 6 become 7, and 7 become 6. So finally we can write this as x of 6 comma 7. So this is what we get here. It will flip 6 and 7, and here also we are getting the same thing. Okay, so I hope you understand and carefully observe. This is whenever all the gates are on one single state, you can apply this technique, taking psi. Right. So let us take the another equivalent circuit, and here we have anti-control and here control, and this is x 1 2 4. So this is nothing but x 2 comma 3. Now we have to show that from this circuit we'll get the same output, and carefully observe the difference is earlier here we have all this one all T gates, but first part is as usual, I think. um, yeah, no, first part is also having a small change. Okay, fine. So let us divide this into two parts, and this is the first part and this is the second part. Now I will explain this, and the next one I'll give you as I will give it to you as a homework. Please try to do it. So let me take the circuit again. Right. So here I have taken the first part. Okay, and all the gates are on first state. That's why I'm taking this as a psi, and these two are 1 and 2. So save. Here we'll get 0, 1, 2, 3 possible cases. Okay. Now I'm taking it directly because already you understand this method. So 0 psi. So here only the operations on psi, but both are off. That's why there is no x gate. So 0. You have to take from right to left. So this is H, T dagger, T dagger, T, T, H and psi. So this T dagger I and everything is gone. That's I, identity operation. And the next one, so in this case, this C naught and this C naught will operate and these two won't operate. So this is a 1 because 1 is on. So H, T dagger, next one off, next one T dagger, next one on, X, T off, again T, next off, sorry, on, H psi. Right. So carefully observe, here we have T dagger square and here we have T square. So I told you already one technique. So this is a T dagger square. So here I'm taking this as a 1 0. Let me write here because it's a safe space is there. So here I'm doing for one side. So this is a T dagger square, that is 100 e raised to minus I pi by 2. And after that we have T square but x. This side x and this side x. T square is nothing but 100 e raised to I pi by 2, but both the sides we have x, that's why no need to multiply, directly e raised to I pi by 2 1, just interchange that diagonal elements, and this is nothing but I 0 minus I. Okay, so this is nothing but I common, that is a z. So finally we can write 1 I outside, H, Z, H psi. H, Z, H is nothing but X. I 1 X psi. That's it. Okay. Next is still not understanding. 2 psi. You please pause the video and try to do it yourself. That is a 2. This time these two on, these two off. So H, T dagger on, T dagger off, T on, X, T off, and again H. So please check. And here side by side and gone. This is nothing but 2 psi. And 3 psi. So this is a 3. All are on, that means H, T dagger, X, that means all C naught will operate, X, T dagger, X, T, X, T, uh, X, H. Okay, so fine. Now here we have some operations here. I hope you understand. Please take like this. Okay, let us proceed. Now here X, T dagger, X. Forget about H and carefully see this T dagger. I'm writing from here 100 e raised to minus I pi by 4, and here x T dagger x, take T dagger but interchange the diagonal elements, that is 0, oh, sorry, e raised to minus I pi by 4 1. Next after that we have T, that is 100 e raised to I pi by 4, and here we have x tx, so interchange the diagonal elements of t, e raised to I pi by 4 1. All are diagonal elements, just multiply. So let's go on 1. Oh yes, 1001 I. So finally this is a h square, h square is also I, that's why it become a 3 psi. That's it. Okay, now we have to take the second part of this. So once again please check what is the result. 0 1 no change, 1 psi, yeah, careful, I 1 x psi, 3 psi no change, 3 psi. Okay, now let us check the second part. Now please take this last state as a psi only. This is the second part of the circuit. Now here we have these operations 1 and 2. First one x 2 comma 3, next t dagger 0 comma 1, again t dagger 2 comma 3, next again x 2 comma 3. Now this time we have t 0 comma 1, first one, and add that to 2 comma 3. Next again 0 comma 2, this time add 1 1 comma 3. So this is x 2 2 3 and 2 2 3. So 2 will become 3, 3 will become 2. And this t dagger t gets cancelled. So finally here we have t dagger 3 comma 2, t of 2 comma 3. Uh, I'm sorry, I think this is a t dagger. I'm sorry. Yes, we made a mistake. One second. I'm sorry once again. So here this is a T dagger. So T dagger, and this is also T dagger. Okay, right. Fine. So this one as it is, 2 3 2 3 cancel, 2 become 3, 3 become 2. So finally here we have T dagger 0 1, T dagger 0 1, that is a T dagger square 0 1. And after that T dagger 3 comma 2 is there, and finally here we have uh, T dagger 2 comma 3, because already 0 1 gone. And after that again we have t of 0 2 and t of 1 comma 3. Fine. Now I am taking 0 psi. Psi no operation, only 0. Okay, so here 0 off, that's why no issue, and here also 0 off, that's why no issue. Next 1, if it is on, take that operation, off, leave it. So 1 psi. So here 1 is on, that's why t dagger square 1 psi. And next come to here, there is no 1, and here 1, but it is off, that's why t dagger square 1 psi, t dagger square, that is uh, yeah, if you want you can write a t dagger square, that is 100 minus e raised to minus I pi by 2, that's minus I hope you understand. So this is 100 e raised to minus I pi by 2, that is minus I 1 psi. Next second, let me write here, here 2 on, that's why t dagger, here 2 off, and here again 2 on t. It's very easy. So this is again 2 psi. Next 3 psi, 3 off, 3 on, that's why t dagger, and t, I mean 3 on, but it is a t, so 3 psi. So which is nothing but 3 psi. I hope you understand. So if it is off, leave it. If it is on, take that operation and multiply. Okay. So that's it. And finally, we got this from 2. Now I'm combining both 1 and 2. And let us check. So here 0 psi, first one no change. So please one more time, please check, no change. 1 psi become this one, be careful. 2 and 3, no change. So second one also no change. And here the first one, this is I1 xi, I1 xi. The second one is this one, minus, because here we have, I think here we made a mistake. This is e raised to minus I pi by 2 is a minus I. Okay, that's a small correction. So minus I. So then minus I gone. That's why, that means 1. this I, and this is a minus I, okay, one state into x psi. So here we have some change. The remaining 2 psi and 3 psi, no change. So now let us take this final operation, that is only one change, that is 1 psi become 1 x psi. So here I can take this psi as a 0 or 1. So see how I am doing this. This is a 2 qubits are there. Okay, so that's why 2 ones are 2 plus a 0. That means a 2, comma 2 plus 1, 3. So this will give either 2 decimal state or 3 decimal state. Okay. Yes. And here, because of this exercise, you will get 0 become 1, first one, here 1 becomes 0. Okay, so this 1 2 qubits, that's why 2 ones are 1 plus 1 3 comma 2. So the finally we got 2 3 become a 3 2. So this total operation can be written as x of 2 comma 3. So exactly whatever we are getting here, this one, right? And the last one I'm giving you as a exercise, so I request you please do that last one, and if you have any doubt please contact. So here I'm giving you as a homework, I request you please try, and please take this as a first part and this one as the second part. And here we have this is 1 2 4, both are anti-control, these are both are anti-control, that's why this is x of 0 comma 1. So finally once you simplify this right hand side circuit, you have to get finally 0 to 1, 1 to 0. So please do it, okay, and take separately first circuit and second circuit and try to do it, and if you are not getting if you are not getting the answer, please contact. Okay, so thank you.